the angle of the decision boundary. Depending on the angle, it will cover the edge cases very well, because the decision score is nothing but the distance between the decision boundary and the data points. Closest data points are farthest, right? That's the large margin classification. So it's going to be better than the logistic regression when compared to the edge cases. The data points which are falling right on the decision boundary are just the other side of the decision boundary. And C is a hyperparameter which will help you play with overfitting and underfitting. And bigger the C, larger the overfitting, smaller the C, smaller the underfitting, right? It's directly proportional. C is directly proportional to overfitting, right? Reduce it, it will reduce. Increase it, it will increase. And scaling is very important. When you do scaling, the angle of the support, the decision boundary changed. The support vectors changed, right? So when you do scaling, it works better. So on KNN, we need to do scaling. On gradient descent, we have to do scaling. SVM, we have to do scaling. Feature scaling is very important. We took this simple data set and built a model. And then we are trying to understand how to do a non-linear decision boundary on a non-linear data. The way we do it is we convert data into non-linear and then do a linear decision boundary. That is how you use linear SVM to build a model on a non-linear data set. Then we understood kernel trick, the most important, I would say, which actually creates a new dimension in the data, right? New dimension in the data in a way. Closest points come closer, farthest points going farther, based on the kernel function. The kernel function is actually inducing that, so that you can actually do a decision boundary there, linear decision boundary. So here you need to do non-linear. You need to do a circle here. But after introducing or inducing the kernel function, it became we were able to do a linear plane, using which we can actually distinguish two classes. So how it works? Simple. Distance metric is what is called as kernel trick. Distance metric is what is a distance formula. The formula to calculate distance is called as a kernel trick. If you use Euclidean distance, you get there is a terminology here: data point and landmark. When you are trying to calculate distance between the first record and all other data, you call this as data point, and all the rows are called as landmarks, including the first one, because we are going to look at the record in itself, record and next record, record and next record. So when you take 5 records, the data set becomes 5 by 5. You take 10 records, after applying kernel trick, it becomes 10 by 10. M number of records you take, after applying kernel trick, it becomes M by M matrix. And the after applying kernel trick, the data becomes intelligent. It knows the records which are closest and the records which are farthest to the data point. Okay. So I have got an idea now. When I was actually talking, right, I've got an idea. Yesterday, one of our old student actually called me and asked me, there are documents and he need to cluster them or group them to different clusters. So maybe he can actually apply kernel trick to find, so you convert the text into numbers and then apply kernel trick and then apply maybe a distance metric, whatever. So anyway, kernel trick is being applied on the input space only, right? So we were not using target variable till now. When you are doing clustering also, you will not have target variable. I think you did not get it, but yeah, I can talk to him. So now we can apply kernel trick here instead of calculating distance, because kernel trick gives you a standardized value between 0 and 1. And the closest points will get 1, the farthest points will get number 0 close to 0. Okay, that's now you understood how the formula is working. This is RBF kernel. So there is polynomial kernel, there is sigmoid kernel. When you say polynomial kernel, right, the function is going to be polynomial equation. In the polynomial equation, you will have x minus L, right? So polynomial equation is going to be first one is going to be x minus L, second one is going to be x minus L square, third one is going to be x minus L cube, like that. Okay, and the RBF kernel will give you one number. Okay, so you can look at the polynomial kernel equation maybe. I too never looked at it. So what is this sigmoid kernel? This is radial bias function and sigmoid kernel. Polynomial kernel. See this? Xi xj plus 1 to the power of d. That's the function. Landmark. One is landmark and one is the xj is landmark. Xi is the current data point. So Gaussian kernel or RBF kernel. You call this as Gaussian kernel also. Okay. So this is RBF kernel. Oh, this is RBF kernel. Both are same actually. Why this guy is confusing? This is just that 1 by 2 sigma square is defined as gamma. That's it. 4.2, 4.3. Laplace. Okay. Okay. Different variant. That's it. Not a big deal. You know, square is not there. So that is Laplace RBF kernel. Hyperbolic tangent kernel. So see on all the formulas you have landmark and x. You are understanding, right? Sigmoid kernel. This is the formula. So formula changes, right? There are different kernels. The formula changes. That's it. Getting it? Any questions?
So how do you know, sir, like when we need to use that which formula?
Good, sir. Good question. I will actually see that again hyperparameter tuning. That's again right the trial and error.
Oh,
We'll see.
okay.
We'll see. Yeah, we'll see that. That's where the grid set CV is very useful. Okay. So we looked into gamma also, right? How the bigger gamma is making the model overfitted and smaller gamma reducing the overfitting. So gamma is directly proportional. You reduce the gamma, overfitting will reduce. Now we have two hyperparameters to tune. On this kernel SVM, right? Kernel trick, we have gamma only. But if you apply SVM also, you'll have C hyperparameter and gamma hyperparameter. Right? You can play with two hyperparameters to reduce and increase overfitting. Okay, bring balance between overfitting and underfitting. Okay, so now let us look at an example, and then I will slow down and we'll discuss. So this is the kernel SVM. To do kernel SVM, right, you need to use SVC class. In the previous example, we used linear SVC. See this? Linear SVC. In the current example, to do kernel trick, we need to use SVC. I did not use it still. Right, so here SVC. Okay. So I'm doing scaling and then I took polynomial kernel here. Okay. In the polynomial kernel, we'll have degree. See these different kernels. See this degree. Right? You specify degree and that's how the distance is going to be calculated. This is not distance basically. When you do polynomial kernel, right, it is actually multiplying the x and the two vectors, the first row and second row, first row and third row, first row and fourth row, first row and fifth row, like that. It is called as uh, vector multiplication. We will see that in once after finishing this, right, in the linear algebra we see the multiplication, right. Let me open that. So this is the next topic, linear algebra. Say vector multiplication it is, and the projection, right? When you do multiplication, you get these projection into the Euclidean the Euclidean distance. So you are trying to measure some kind of the projection kind of thing between the two vectors when you are doing polynomial kernel. Okay, so I used polynomial kernel here. If you want to use the RBF kernel, right, you need to specify RBF here. Okay, these hyperparameters are there in the API. You look at it, right? And then I am passing degree from 1 to 9, C parameter 1 to 9, and coef 0. There is a coefficient. There is a parameter called as coef 0 for poly, right? That is from 1 to 9. So that coef 0 will work as a regularization parameter in polynomial kernel. So when you are using polynomial kernel, the cast function will have coef 0 as a regularization parameter. What is regularization parameter? How will it help the model? What is regularization parameter?
Sir, here standard scalar.
Hmm.
Standard scalar also regularization, sir. You are using for regularization, right?
No. Scaling, data scaling,
Scaling,
feature
feature
scaling.
scaling. Your feature
Ah,
scale. Okay.
0 to -1 to 1 or -2 to 2, or
Yeah.
it doesn't matter. It matter. It actually depends on the data, right? So when you do standard scaling, it will calculate z-score. Maybe for some cell, right, the z-score may be 10,000. For some scale, in some data, z-score may be between -5 and +5 only. It depends on the data, how variant the data is. The z-score will vary like that. Got it?
Yes, sir. Yes, sir.
So the regularization, you remember what is regularization and what it does to the model? Regularization actually makes the curve smoother, right? So when degree is high, regularization tries to reduce the complexity. That way, the model balances, gets balanced. So C hyperparameter actually influences the SVM algorithm, and the coef actually influences the polynomial, right? On a RBF kernel, you will have gamma. On a polynomial kernel, you will have coef 0. Let me show you that. See this on a so here's coef 0. Yeah, see this coef 0. Independent term. Sorry. This is not. Sorry, I am really sorry. So this is not the regularization parameter. Gamma is the regularization parameter. The coef 0 is the independent term. This is the uh, intercept. Okay, this is intercept in polynomials. So here, right, this is 1. If you want to change it, right, you can change it. If coef 0 is given a different number, it will take that. That is independent term. Okay, got it? Sorry to confuse you. This is the regularization parameter. Gamma is the regularization parameter, which actually tries to make the model smoother. Got it? So this coef 0 will work only for poly and sigmoid kernels. Other kernels it will not work. RBF poly sigmoid only we have implementation. It's scikit-learn. Okay. So we have now built the model, right? We design the model, and then we are using grid set CV, the pipeline, and then the hyperparameters, right? Fitted best parameters, best estimators. But give me 1 second. Yeah, sorry for that. So we took the best estimator. This whole process is same, right, for all the algorithms. If you look at it carefully, right, before the building the algorithm, depending on data, the pre-processing will change. After building the data, making the model the best, the process will change. But this code will not change. This is copy paste code. This is all is copy paste code, right? You can just copy paste it. But when you know the algorithm and the details, right? What is gamma, what is coef 0, what is C, what is degree, then you will be able to play with the algorithm and make the model the best. If you don't know those things, right, you will not be able to do anything. That's where I spent a lot of time in explaining the algorithm, right? So I hope you got the whole essence of the algorithm. When you look at this code, right, we are not doing anything big. We are just using those parameters and trying to play with, right? So when you know what they are, how they react, you'll be able to play with them well. Okay, now I tried to this code is from Alan Giron's book, right? I did not wrote the graph generation code. It is just for visualization we are showing, but in real time we will not do this. We will never do a visualized diagram like this after building a model, because there will be many columns and the data set is going to be huge, and there will be many problems if you want to do this kind of a thing. So that is the kernel trick. The use of kernel trick is when you have more columns than rows. Then when you apply the kernel trick, it becomes rows by rows matrix. The dimensionality reduces. And while applying kernel trick, you are not looking at y value. Right? You are just trying to extract the essence into the data set, into the input space, using input data only. You remember that. Okay. While building a supervised model, whether it is SVM or a linear regression or logistic regression, the algorithm is considering y value and trying to generate the model, right? Generate the coefficients or whatever, right? Understood? Any questions? This book is very good, but when you know the fundamentals, right, it is good. Right? This guy did not cover all the fundamentals. He actually gave the total process and the code examples and many things there, but we didn't went into the details of how exactly the kernel trick works, and this whole stuff is not there. Okay, there is a lot added to whatever is present in this book, in this course. But out of all the books I looked into, this is the best. And Andrew is theory, and this guy's code examples are the best. I found. So that's where I kept it in the notes also, so that you can buy if you want. It's an expensive book, around 2,500 rupees. No need to buy. No, that's for sure no need to buy, because we covered all. Beyond what is there in that book, we covered it. Okay. So, any questions on SVM? If we are good, right, I'll jump into the next topic, the linear algebra, which will be used in the coming topic, clustering, sorry, dimensionality reduction. Principal component analysis and dimensionality reduction are heavily dependent on linear algebra. So I'll jump into linear algebra. Any questions here?
So the kernel trick is also a kind of dimensionality reduction, right?
Kernel trick is dimensionality reduction only.
Okay. So, but it is not using linear algebra much.
Here actually it is linear algebra only, right? This is not linear algebra, but it is math only, right? So if you look at the the distance calculations and all that, this is math only, right?
Yes, it is math.
It is math only, but you know, in the actual dimensional principal component analysis, right? There will be more mathematics, the eigenvalues, eigenvectors, singular value decomposition. Those concepts will come. We'll see, right? So, shall I move on? Okay, I got it. So we need to understand a little bit of linear algebra. So linear dependence and linear independence, vector multiplication, what is unit vector, what are orthogonal vectors, right? These are all concepts we need to understand. When we understand orthogonal vectors, right, I'll come back to the polynomial kernel and try to show you something there. Okay. So I hesitated a little bit because you don't know what that is. Okay. So remind me if I'm forgetting. So linear independence and linear dependence. It is simple. You have two columns in your data set. One is the SFT area in feet, another in the SFT area meters. Are they both strongly correlated? Should I repeat the question?
Yes, they are.
Yes, sir.
There is one column which is in SFT, and the other column in meters. They are same data in different units. If you multiply one with other some number, right, you'll be able to generate the other, right? So that is called as linear dependence. Correlation is called as linear dependence. Strong correlation, 1 or -1 correlation is called as linear dependence. Okay, if that is not there, then you call it as linear independence. You take these two columns, two vectors, we call them as vectors because we are representing it as a column matrix. Okay, you multiply first vector with 2, you will get second vector. V2 is equal to 2 into V1. These two are linearly dependent. Strongly correlated columns are linearly dependent. Okay, if you look at the linear regression algorithm, dummy variable trap, in linear algebra, they write in linear dependent, linear independent terminology. If you look at the same concept in linear regression in machine learning, they write it in correlation, strong correlation, strong not correlation. Right? So same concept. Two people write it in two different ways. Okay, because their backgrounds are different, and some people want to confuse other people so that people feel that you are great. That's there in science community and mathematics community. That is there. People want you to be the person to be a great person, even though there is nothing. Is there anything here? There is nothing. You take one vector, multiply with other number, you are getting another vector. It is linear dependent. If you are unable to do that, it is linear independent. If you take these two vectors, no way you can generate other vector by multiplying or adding or whatever manipulation you do. Okay, so they actually came up with a kind of mathematical theory there on based on this concept. So vectors v1, v2, and so on, vn are linearly independent if the linear combination is equal to 0. Somehow you take some coefficient, multiply and add, you get 0. See this here? You multiply with -2 on v1 and add v2 plus -2 v1, you get 0. 0 vector, all zeros. Do you agree? 2v1 minus v2. 2v1 minus v2 is 0, 0, 0. Right?
Yes, sir.
So the 2, right? A1 is 2 and A2 is 1. A1 is 2, A2 is 1. So there are coefficients which make the linear combination, we call it as linear combination 0. Then you call those vectors as linearly dependent. When a linear combination becomes 0, you call those vectors as linearly dependent. Okay, so I have taken some examples here to show you what is linear dependence and how do you find on a huge data. So here there are only 3 values in the vector. So okay, that's okay. But so these are rows actually. This is first row and this is second row. I am representing them as vectors because this mathematics actually supports. Initially, when we actually looked at x transpose, theta transpose x, we don't know why we were actually representing our matrix as vectors, right? To support, mathematics, they talk about vectors. So to actually accommodate that, the people, whoever is trying to write theory, right? They try to represent rows as columns and try to do theta transpose x and all, okay, for theoretical purposes. Okay, so there is no practical problem there. You can do x theta, then also you will get predictions. If you don't transpose the rows as columns, you calculate x theta, then also you get predictions. If you transpose x, then you have to do theta transpose x to get the predictions. I hope you got it.
It is actually should be told as theta transpose x transpose, right? Why we are not telling x transpose even though we are doing the x transpose?
Yeah. Yeah, these are all, Einstein wrote something, write something, right? It becomes the great thing. If I write it, if you write it or I write it, right? Professor will definitely catch hold of us. Right?
Yeah.
So that's the world. That's how the world works, right? So we should not question. We should follow, right? We just because it's a convention. Everybody is following. We are also following. So it's convention and confusion also. So that's all. So I took some examples of linearly dependent and linearly independent vectors. So I have taken v1, v2, v3, and I am trying to see, whether it is linearly dependent or independent. Okay, whether these 3 vectors are linearly dependent or independent. If you have 1,000 rows, this is how you do. Okay, so you take a1, a2, a3, right, and create a linear combination and try to find those a1, a2, a3s. In this particular example, a1, a2 are very simple. A1 is E2, A2 is -1. Simple, right? It's evident. But in this, right, you cannot find that by looking at the vectors. So you need to create a linear combination like this. A1 into vector 1, A2 into vector 2, A3 into vector 3 is equal to 0. And then solve the equations. If you multiply these, right, A1, 2A1, A1, 4A1, 0, A2, 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 2A2, 2A3, 0, A3, 7A3, right? You can actually represent as them as linear equations. Right? I was in 8th class, 9th class time frame, right? I actually studied these. I don't know why I was actually looking at them. Now I know, right? That's another, exciting thing for me because after around 30 years, maybe 35 years, I was actually able to use what I learned, right? So nothing got wasted. That's an important thing. So I now I am solving the equations to find out these a1, a2, a3 values, right? You need to solve the equations, right? So I have taken the second equation and the third equation, solved them, right? And then I took the fourth equation and the second equation, third equation, solve them. I've got equations in a1, a3 terms. I solve them. I've got a3 is equal to 0. I substituted that into one of the equations. I've got a1 is equal to 0. So all coefficients are 0. Right? So they are independent. Okay. So if you look at this this definition, right? A1, A2, A3 are linearly independent only when you do linear combination, all the coefficients are 0. If one of the coefficient is not 0, then you say they are dependent. In this case, both are not 0. right? 2 and minus 1, right? So here all are 0. So they are independent, linearly independent. Only coefficients are 0, then only you are able to produce 0. Otherwise, you are not able to produce 0. Linear combination of the vectors, you are unable to generate 0. That means you multiply with any numbers on these vectors and do linear combination, you are unable to produce 0. Okay, so that is linearly independent. So I have taken another set of vectors and tried to do one more, and I have got coefficients here. See that a3 is equal to 1, a1 is equal to minus 1 by 2, a2 is equal to minus 5 by 8. If you multiply these three vectors with those three coefficients, you will be able to produce 0. That means you are able to generate this vector by multiplying something with this some number with this vector and this vector. That means they are having some correlation. It may be multicollinearity or correlation, strong correlation between two columns. Right? So that is linearly dependent. Got it? Basically correlation, non-correlation. There is 1 minus 1 correlation and multicollinearity. Right? Multicollinearity is called as linearly dependent vectors. Right? Non-collinearity is called as independent vector. Got it? Can I move on? So I tried to show the same thing in equation, okay, in a mathematical theory, kind of thing. If you understand the concept, that's enough. But this is just out of my finicky nature. I did it. A vector with at least one non-zero value is said to be a non-zero vector. A vector is called as a non-zero vector when at least one value is non-zero. Right? This is a non-zero vector. Okay. If all are 0, then you call it as zero vector. Okay. And the set containing 0 vectors is always linearly dependent. The set containing 0 vector. That means you have 4 vectors like these, right? One of the vectors is having zeros, all zeros. K1 is 0, K2 is 0, K3 is 0. Then this whole set is called as linearly dependent. Because you multiply the other vectors which are non-zero with 0, right? And any number, you take some number and multiply the 0 vector, this is becoming 0, right? In this linear combination, this term is becoming 0. You take any number, multiply that with 0 vector, you get 0, right? Even if you multiply with 0 other vectors, the total thing is becoming 0. So there is a non-zero coefficient for one of the vectors that becomes linearly dependent, theoretically. Got it? A set containing a 0 vector is always a linearly dependent vector set. Got it? Did you get this point? Should I move on? Yes, no?
Yes, sir.
Yes, sir. As you said, it looks like theoretical use only, but in real time, so let's say if we take K1,
We will
K2,
not.
K3.
We will not take that column. We will eliminate it and try to do.
Yeah.
What?
Yes.
I am saying this. I wanted to show you rank of a matrix. For that, I am actually trying to build a background.
Okay.
The foundation. A set containing m number of n by 1 dimensional vectors is linearly dependent if m greater than n. Right? Number of columns are more. See this here, n by 1 dimensional vector I said. M number of vectors I said. Right? M number of rows, each row having n values. M number of rows, each having n number of values. So each row I represented as a vector. Okay. So if number of columns are no, I shouldn't be talking about columns here. Right. So number of vectors are more than the values in the vectors, then it is linearly dependent. Okay. So 4 vectors with 3 by 1 dimension. right? We call three dimension, the dimension of a vector is 3. This vector's dimension is 3, we say. This vector's dimension is 3. When you say vector, only one column is going to be there. When somebody says a dimension 3, that means 3 values are there. Okay, dimension 3 means 3 values. Dimension 10 means 10 values. On a vector, you will have only one column. Okay. If a set of vectors are linearly independent, then removing one arbitrary vector will not affect linear independence. If there are a set of vectors, right? So you suppose that you know these three vectors are linearly independent. If you take out one of the vectors, even then they stay linearly independent only. Okay. So a set containing unit vectors. See this, I am calling them as unit vectors. What is unit vector? If you calculate norm of this vector, right, you will get 1. What is the norm of this vector? Can somebody tell me? Norm of this vector? Unit vector. Right?
Is it
Norm of
square root of all the values?
square root of 1 square plus 0 square plus 1 0 square. Square root of 1 square plus 0 square plus 0 square is called as norm of a vector. Length of the vector or norm of the vector is same. Okay. So set containing distinct unit vectors, right? This is unit vector, unit vector, unit vector. Because when you calculate norm, you are getting 1. Square root of 0 square plus 1 square plus 0 square is square root of 1 square is 1, or square root of 1 is 1. Like that here also. So now let us understand what is rank of a matrix. Okay. When we actually look into NLP, we'll see rank retrieval model. Okay, that rank and this rank are different. This is matrix rank. Okay, we need to understand rank because eigenvectors, eigenvalues use a little one place they actually talk about rank of a matrix. That's where I'm trying to explain. So rank of a matrix is defined as maximum number of linearly independent column vectors in a matrix or the maximum number of linearly independent row vectors in a matrix. Both definitions are equal, but whichever is low we'll take, right? The maximum number of linearly independent column vectors. So take a matrix A with m number of rows and n number of columns, right? And then if you find r number of maximum independent rows, c number of maximum independence columns, then rank of a matrix is going to be minimum of m comma n. Right? So minimum of these two, right? So if r is less than c, r is going to be the rank. C is less than r. Simple. It is very simple. So if you look at this matrix, right? So maximum number of linearly independent vectors here are 2. Independent rows are 2. Okay, columns are 4. The rank becomes 2. So whichever is minimal, we take that as rank. Okay, first you need to calculate maximum number of linear independent columns. Then you need to find out linearly independent rows. Whichever is less, that becomes the matrix. See this, rank of A is equal to R if R less than C. Rank of A is equal to C if C less than R. Okay, R is the number of independent rows. C is the number of independent columns. Got it? Simple, right? So,
can you just show that to the example once again, sir?
Yeah, I'll show that. I'll show that example and come back. So rank of A is always going to be less than minimum of m comma n. Right? So if you have 4 rows and 3 columns, it is going to be less than or equal to 3 only. Let me show you. So this is called as row reduction echelon form. Okay, I am actually covering most of the linear algebra in 1 hour. Okay, it's a fast track course on linear algebra, but this is enough. Whatever I covered here, if you understand, that is enough. Don't go into linear algebra, it will take 2 years again. So linear algebra, right? How to find rank of a matrix? So when you are solving equations, right, you are actually trying to find rank only. But the solving thing can be done using row reduction echelon form. We call it as row reduction echelon form. This one, whatever we are doing right now. So I have taken this matrix and flipped C3 with C1. Right, column 3 is 1 4 0, column 1 is 4 6 2. I just flipped it. See this, 1 4 0 came here, 4 6 2 came here. Okay, and then I am subtracting R2 for R1 by multiplying with 4 from R2. Right, R2 I have taken. Right, I multiplied the first row with 4, subtracted it to so that I can make this particular cell 0. I am actually trying to make some cells 0 so that I'll find the independent vectors. See what I'm doing here. I took this vector, multiplied with some number, right? And I took this vector and subtracted. So this is linear combination, right? Linear combination of these two vectors. Okay. And then now the next operation, right? I took the R2, right? This vector, and then divided that with 5. And now 1 by 5, I multiplied this vector with 1 by 5 and then added it to 4th row and replaced it with the 3rd row with that. So it's a linear combination again. So I got zeros there. So somehow I was able to eliminate the one row, right? So that means this is actually having some dependency with the other rows. This row is having dependency with other rows. So I tried to do the same thing with columns also. I was able to eliminate one number only, but unable to eliminate this number. If I was able to eliminate that number also, right, I would have got 3 independent columns and 2 independent rows. But now I've got 2 independent rows and 4 independent columns. Okay, 2 independent rows. After doing this manipulation, right, I've got 2 independent rows and 4 independent columns. The rank of the matrix becomes 2 because we'll take the minimum, right, of the independent rows and independent columns. Minimum of independent rows and independent columns. Got it?
Yes, sir.
So the same thing I showed it. See this here. R is the independent row, C is the independent columns. If R is less than C, you take R as the rank. If C is less than R, you take C as the rank. Okay. And anyway, when you actually apply row reduction echelon form, it is going to be less than M or M, right? Minimum, right? So rank is going to be anyway. Simple, right? Simple math it is. Any questions here? This is called as row reduction echelon form. Now, solving equations can be done like this also. We are actually solving equations here, right? So this thing can be done like this also. Yeah. Good.
Here are we trying to only reduce the rows or both the rows and columns?
Both rows and columns. We tried, initially I tried to, flip it and tried to do the operation in such a way that it actually reduces rows and columns both. But this one survived. Right? It doesn't matter. We are trying to nullify the rows and columns so that we'll find ultimately the numbers there. When there are numbers, they are independent. When there are no numbers, it is a dependent one. This is dependent on these two rows. That's where it actually got eliminated when we applied some linear combinations. Right? So now vector algebra. So how to multiply two vectors? We know this. We actually seen it. Right?
1 second, sir.
Yes, please.
Regarding the rank finding, the purpose of finding rank we are yet to discuss.
Yes, sir.
Okay. Sure.
So in eigenvectors, eigenvalues decomposition, you get the number of eigenvectors which is equal to the rank of a matrix. Okay, we'll see that in a moment.
Okay.
In coming class. So here, yeah, this is all theory, and we'll actually consolidate everything when we actually learn the eigenvalues and eigenvectors and singular value decomposition. Most of it is not important for the interviews. Most of it is not going to be used in our real time. But when you look at the theory, right, you should understand when you are actually studying some concept somewhere, maybe something new was found, new will be found in future, right? Then you are actually looking at it, you need to be able to understand. So for that purpose, I am explaining this. Okay. So I take two vectors, right? V transpose V1 transpose V2 is equal to V2 transpose V1 when you know commutative, right? So these are like matrices, right? You transpose it, you multiply, you get one number. When you multiply two vectors, you get one number. This point you need to remember. I think we used it even before also. When you multiply two vectors, you get one number. Where we used it? Here. Right? Here. So when we, when you apply, RBF kernel, you get, but in a polynomial kernel, if you look at the function, see this, you are multiplying two vectors, you get one number, plus whatever the coef 0, you add and you actually apply the power, and between two vectors, always you get one number, in this cell, whether you apply RBF kernel or a polynomial kernel or whatever sigmoid kernel, you will get one number only. Okay, so that's kind of whatever use, right? It's going to be used in many places. Undercurrent it is. When you multiply two vectors, you get one number, and that's going to be commutative. And then we have used this also in SVM when we were actually explaining. Norm of a vector is the length of the vector, basically. So this is V1. If you take a data point, right, this vector can be represented as a data point. You say it is a vector when it has got the dimension and the direction and magnitude. So we are saying from origin it is going in that direction. If this V1, V2 is somewhere here, we'll say from origin it is going in that direction. Okay. The length of the vector is going to be square root of V1 square plus V2 square. It is Pythagoras theorem. Right? This is V1, this is V2. This length is going to be V1 square V2 square, square root of V1 square V2 square. So this is also called as norm of a vector, L2 norm of a vector. Have you seen L2 norm somewhere? Have we seen L2 norm somewhere? Do you remember?
I think lasso.
Regularization. Ridge regularization is L2. L2.
Okay, region lasso.
Yeah, that's good. You're 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 vaguely remembering. That is good. So L2 norm, we call that as L2 norm or no ridge regularization because of this is L2, right? This is L2 norm. L2 norm or length of a vector are same. Okay. So that is another concept we should remember. Unit vector. Any vector can be converted to unit vector when you actually normalize. Right? How do you normalize? You take length of the vector and divide the vector like this, it becomes unit vector. This is normal vector and we converted it into unit vector. This concept is very important. This will be used again in NLP, natural language processing, information retrieval. We will try to find out the distance between two vectors. So then you actually convert your vector into unit vector and try to do the distance metric. Okay. So you take the V1, V2, you divide it with your length, then it becomes unit vector. How? See this, how do you decide whether a vector is a unit vector or not? By calculating the norm, right? What is unit vector? The length is going to be 1. Right? This length should be 1. So how will you get length? It is norm of a vector. You take this vector and try to calculate norm. It's going to be square root of V1 square plus V2 square. Do you agree? For this vector, let me try to write it down and explain. See, I think your homework is increasing a lot, right? Now it piled up like anything. Right? Do you agree?
Yeah, we are really worried, sir. At least I'm really worried.
Yeah, everybody is like that. Sir, I know, right? I have seen many batches, right? So by this time, it is going to be heavy, right? That's where I say try to practice, and you need to spend at least 3 hours. But 3 hours is not enough. You have to spend whole weekend and every day 2-3 hours. Then you will be able to cover it by end of the course. So we are actually dumping like a year and a half course in 4.5 months. This is just like we are at 30%, 40% at the course. We have many things to come. So fundamentals are covered, and I am actually jumping into the real whatever. Okay. So if you see this, right, if you have to calculate the length of this vector, it's going to be square root of v1 square plus v2 square. We don't know whether this is 1 or not because we don't know the values. But even when you don't know values, you can measure whether a vector is you can actually see whether a vector is a unit vector or not. If the total thing becomes 1 like this, right? So when I divided these values with the length, suppose that this is 5 and 6. Okay, the vector is 5 and 6. If you calculate length, right, it's going to be 36 plus 25. Can I do 64 and 36? No, I don't. So it's square root of 20, 56,
3 and 4 you can do.
61, 3 and 4. Okay, 3 and 4. Yeah, 9 plus 16 is 25. Yeah, that's good. You read my mind. So 5, right? So I have got the length of this vector is 5. So this is not a unit vector. So can I convert this into unit vector 3, 4? Yes. Right? 3 by square root of 3 square plus 4 square. Right? 4 by square root of 3 square plus 4 square. If I do this is a unit vector. This is a unit vector. How can I say? This is going to be 3 by 5. Right? This is going to be, it's going to be 4 by 5. I am saying this is a unit vector. How can I say? If I calculate this norm of this vector, right, it's going to be 1. Square root of 3 square by 5 square plus square root of 4 square by 5 square. Right? It's going to be 3 square into 5 square plus 4 square into 5 square divided by, oh, sorry. 3 square plus 3 square plus 4 square divided by 5 square, right? It's going to be 25 in the numerator, right? Divided by 25. You got 1, right? I converted this 3, 4 vector with a length of 5 to 1 by actually dividing it with the norm of the vector. When you divide the values with the norm of a vector, then the vector becomes unit vector. So theoretically also the same thing. See this? Whole square, and then the square root is gone. Right? The sum, you get 1. Got it? Got it? Yeah. So this is very important. That's why I'm actually stopping here. Unit vector is very important. We'll use it many places. And then we have seen projections, right? In our SVM, right? We have seen that projection. The data. You take the weight vector, and then you take the projections of the closest data points, and you take the maximum projection. That's going to be the decision boundary. So how it is going to know whether it is maximum or not, how to calculate projection? This is how it is. So V1, U, V and U are two vectors, and V is being projected to U. This red distance is the red colored distance is the projection, right? P value. P value can be found out by U transpose V by length of U. Okay. If the vectors are on the opposite directions, right, you will get a negative projection. So this is the projection. So you extend this vector in the negative direction and then take the distance there. That is called as negative projection. This is not that important. Diagonal matrix and identity matrix. You all know this. See this? There are values in the diagonals, right? other values are 0, then you call it as diagonal matrix. See this here? All the other values are 0, only diagonal values are non-zero. Then you call it as diagonal matrix. Right? Unit matrix where diagonal values are 1. Use of unit matrix also you know. A into I is equal to I into A is equal to A. Right? This is unit matrix. And then there is a concept called a singular matrix. Do you remember what is singular matrix? Did I explain this before? Did I explain singular matrix before?
I think just only one element in the matrix.
No, sir. Do you remember dummy variable trap?
Yeah, we discussed that. You discussed.
We discussed it, right? When matrix is having purely dependent vectors, when you try to calculate x transpose x, you will get a singular matrix, and you will not have inverse for a singular matrix, right? So that concept. What is singular matrix? This matrix is singular, right? How to calculate inverse first, right? You take A, B, C, D, right? 1 by AD minus BC, D minus B minus C, A. This is inverse of this matrix. Okay, these inverses are used in even computer vision also. Okay, someday, right, when we actually look at the deep learning, I'll explain you how we actually did maybe half an hour, maybe 15 minutes. I'll explain how we actually implemented this speed detection system on NTPC premises. Okay, theoretically, right, how did we do it and all that. If you have interest, right, you can actually experiment with it. Okay, so inverse is also very important. I took only simple matrix here because you should know what is inverse, what is determinant. This is called as determinant. 1 by AD minus BC. This AD minus BC is called as determinant. Okay, so you calculate a determinant, you divide that with D minus B minus CA, you get the inverse. When you multiply this matrix and the original matrix, you get I. A into A inverse is equal to I. Identity matrix you get. You multiply these two matrices, you get identity matrix. So when there is no inverse for a matrix, then that matrix is called a singular matrix. When there is no inverse, you take one matrix and you are unable to calculate inverse. When will you be unable to calculate inverse? When the denominator is 0. If you get this determinant 0, right, then you will not be able to calculate inverse of a matrix. So that matrix is called a singular matrix. So can you calculate inverse for this matrix? Can you calculate inverse for this matrix?
No.
No, right? So the determinant is 0. If you try to put determinant 0, 1 by 0, minus 1 by 0, 3 by 0, sorry, 5 by 0, minus 5, minus 3 by 0, D, right? Minus B, 3 by 0, minus 5 by 0, minus 3 by 0, and 5 by 0 you get. Divided by 0 is not defined. So you cannot calculate inverse for this matrix. These kind of matrices are called as singular matrices. Okay. So when you have two strongly correlated columns, see this? They are strongly correlated columns. You try to calculate inverse, right? You get a singular matrix. Sorry, the two strongly correlated matrix itself is singular matrix. Only strongly correlated columns are there, then it is definitely singular matrix. But some columns are not strongly correlated, some are correlated. You do X transpose X, it becomes singular matrix. You multiply the same matrix with itself, even when there are some not strongly correlated columns. Right? Suppose that the matrix is like this: 1, 2, 3, 8, 9, 10, 5, 3, 3, 5, 3, 3. Right? So these two columns are strongly correlated, but these two are not. Right? Even then, if you actually do X transpose X, you take the same matrix and multiply it itself, the resultant matrix is going to be singular matrix. That's what we have seen in linear regression normal equation. Okay. I hope you got it. Now this is yeah. Any question?
No, we discussed this, sir. You said if they are related, in that case we'll get the
Yeah.
determinant. Yeah.
So, symmetric matrix. Symmetric matrix, you see the upper triangular values and lower triangular values are going to be same. Have we seen symmetric matrix before? Have we seen?
Heat map.
Heat map.
Heat map. This is same heat map I kept it here. So correlation matrix is a symmetric matrix. Okay. So if you look at the lower triangular, upper triangular, it's going to be same. Even yeah, when we try to do confusion matrix, is there symmetric matrix on a multi-class classification? Multi-class classification, confusion matrix, is that a symmetric matrix?
Yes, sir.
That's
If it is
right.
mod is working fine, then it is yes.
No, even when model is working fine or not, it is symmetric matrix only, right? Because class 1, right, tries to look at how it is being classified, predicted as class 1, class 2, class 3, class 4, class 5. Again, class 2, class 1, here class 2, class 1. I think it is symmetric. We need to think a little bit or look at it. I think it is. Maybe wrong, maybe right. Yeah, you look at it later. So the matrix of distance matrix. If you take two cities, maybe 5 cities, and you wanted to calculate distances between cities and cities, right? It's going to be a symmetric matrix. So Aij is equal to Aji. Ij is 1 1, right? Or 1 2 is equal to 2 1. Oh, sorry, 2. This is 2 1. Second row and first column. 2 1 is equal to 1 2. 3 1 is equal to 1 3. Like that. This is symmetric matrix. Now we are getting into the eigenvalue, eigenvector, but time is up. And I'll talk about one concept called as orthogonal vectors. I'll upload this, have a look at it. Monday we'll actually see. It is the orthogonal vectors. Yeah, this is orthogonal vectors. Right? Two vectors u and v, multiply them together, you get 0. They are called as orthogonal vectors. What is orthogonal vector? Is one vector is perpendicular to the other. Okay, one vector is perpendicular to the other. That is orthogonal vector. Okay, when you are doing the polynomial kernel, right? If they are orthogonal, right, you get 0 value here, and only the coef 0 to the power of whatever is going to the value. So when two vectors are orthogonal, that means two rows are completely different. Then you get less distance. When they are kind of similar, right? You get more distance. So this is actually distance measure. Again, polynomial kernel also. When you know the orthogonal concept, orthogonal vectors concept, right? You will understand why that equation is actually measuring the distance. Okay, two vectors you multiply, you get 0. They are called as orthogonal vectors. Okay. So we'll talk about this maybe Monday. So any questions so far? Sorry. So you go through these notes, and this notes is enough. Okay, don't go into. If you have time, you go into it. But practice, complete the practice, and then go into whatever you want to. Okay.